Okay. So hello. So this is my next video. I recorded this video, but I forgot my mic wasn't on. So yeah. So okay, last video I ended off talking about writing linear systems as matrices, and how it's basically the fundamental principles of linear algebra. So now we need to be able to do things with those matrices. We need to be able to actually find the solutions with those matrices. So how do we do this? We use row operations. And we use those row operations to get the matrices in REF or RREF form using Gauss and Gauss-Jordan elimination. Gaussian elimination will get our matrice in REF form, and Gauss-Jordan elimination will get our matrice in RREF form. We can do this by doing row operations. So uh, for addition, we add two rows, and that becomes the row. And we subtract two rows, and then that becomes the row. So R1 minus 3R2 would mean that R1 is becoming itself minus 3 times R2. That's how we denote that. So if you're showing your work on a test or by yourself or just to like look back on it, this is how you would write it. You would say R1 minus 3R2 if you want to subtract 3 of R2 from R1. We can also interchange two rows, even though it doesn't do much, but in some cases where you have, you'll see a leading one above or below where it needs to be, you can interchange two rows. You can also use scalar multiplication. In most cases, you can use scalar multiplication, but just to multiply one one whole row by some constant, if that works for you, to get a 1 or some number. Okay, so our first example is solve the following matrix using Gauss-Jordan elimination. So if you want to, and you can pause the video and try this for yourself if you think you can do it already. I'd be surprised, but um, basically what we want to do here is we want to get this in RREF form. So even though you don't necessarily know what that looks like, you want to get it in a form where it basically tells us exactly what the solutions are without us having to guess or solve for anything. So what you need to do is you need to add and subtract rows from each other to get a matrix that will give us the solutions. So after doing some row operations, and you might have been able to do it yourself, you're going to get this matrix down here. And it turns out this matrix is super key. This is the identity matrix for a 3 by 3 on the left. That coefficient matrix is in RREF form. So it basically it tells us exactly what the solutions are. And in this case, since the right-hand side is 0, 0, 0, it tells us that our solutions are x equals 0, y equals 0, and z equals 0. Each column represents each variable. So and it could be an RREF form, but the right-hand side could be 4, 1,000,000, and 10 for the solutions. And it would just mean x equals 4, y equals 1,000,000, and z equals 10. See how that works? Okay. So our next example is convert the following matrix to REF form, not RREF form, using Gaussian elimination. And so if you do this and you do it by yourself, if you want to solve it by yourself, don't look at the bottom of this slide, but you're going to get the following matrix. 1, 1 half 3, and then 0, 1, negative 5, 4, 0, 0, 1. Then on the right of our augmented matrix, which remember is just A, line B, we're going to have 2, negative 1/4, and 38 over 15. Now it's in REF form and can be solved using back substitution. That's how we're going to get to RREF form. So REF form is, in a sense, in most cases, you'll see where it's not, but it is usually inferior to RREF form because we have to back substitute to find the solutions. But essentially, if we back substitute to find the solutions, we're converting it to RREF form. It sounds confusing, but you'll see. So let's say we want to convert the following augmented matrix to REF form using Gaussian elimination. So we have the matrix 1, 3, 4, 3, 1, 2, 7, 1, 2, 8, 9, 2. And after you do that, you need to put the matrix in RREF form. So this exercise should essentially show you the connection between the two. They're pretty much the same. It's pretty easy to get it in RREF form after you get in REF form. but the RREF form is a lot cleaner and tells us a lot more about the matrices than REF form. If you don't want to see the answers, pause and do it yourself. Okay, now I'm going to the answers. So the answer to the first one, you see here, we have the bottom triangle of zeros, and then we have the diagonal line of ones, and then we have our numbers 4, 9 halves, and negative 5 fourths on that top row. So if we wanted to find the solutions in this case, since it does actually tell us that z equals negative 8 over 7, we would have to plug in z, then we would have to solve for y. Then we would have to plug y and z back into the first row to solve for x. And then we would have x, y, and z. But using Gauss-Jordan elimination, when we get an RREF form, it's going to tell us literally 1x equals 83 over 7, so x equals 83 over 7. 1y equals negative 10 over 7, so y equals negative 10 over 7. You see how this works? So 1z equals negative 8 over 7, so z equals negative 8 over 7. Remember, this is still just a coefficient matrix. That's what it represents. Because we could solve this using systems and elimination and everything, but that's what a matrix is doing. It just is a brief explanation of the system, if that makes any sense. Okay, so that's the end of this video. Next video, I'll go more into matrix operations and how we can manipulate matrices as just a whole to solve for some representation of a matrix. Multiplication of matrices, the transpose, the trace, scalar multiplication, everything. So stay tuned for that video. Thanks for watching and have a great day. Thank you.